Hello everyone. Our presentation today is going to revolve around the paper Learning to Cache with No Regret. Before we get into the crux of the paper, let's understand what caching is. Well, caching is this temporary storage where we store frequently accessed data in a fast accessible manner. How do we decide which files gets to be in the cache and which files don't? We use something called caching policy in order to make that decision. Some of the commonly used caching policies are LRU and LFU. LRU removes the least recently accessed item, whereas LFU removes the least frequently accessed item when the cache is full. We use a metric called cache hit ratio to evaluate their performance, and based on which we can say which caching policies work better because their performance depends upon the distribution of the files. The paper tries to answer the questions raised by the metrics and the need for a universal caching policy by introducing a metric called regret. In simple words, regret can be explained as something I would have done differently had I had the chance. The reason why this regret metric works is because it pushes the caching policy and the algorithms to be more optimized, to be more efficient. And it also tries to strike a balance between the popular files and exploration of new files. It advocates for the suitability to accommodate diverse caching scenarios and request distributions. In order to present a structured, adaptable model, the paper presents something called online gradient ascent algorithm. As we said, a caching policy makes a decision of what stays in the cache and what doesn't. Well, the OGA algorithm works on the assumption or works on the popularity of files. We know that the popularity of files changes with time, and the OGA makes the caching decisions based on this gradient ascent in an online learning framework. This is for a singular cache. Can we expand it to a network of caches? Well, yes. We do it with the help of a bipartite graph, and we call the algorithm to be bipartite subgradient algorithm. Just like the OGA, we initialize the cache, we observe the file request, compute the subgradient, and then run the OGA locally. The performance of the OGA or the bipartite graph is significantly better than LRU or LFU. So, what does it mean for the industry? Well, with this new uh, caching policies, you can say that the improved cache performance can lead to faster content delivery and reduce latency. We know that faster content enhances the user experience while leading to user engagement and retention. The caching policies such as the OG and BSA reduces the load on the origin servers and content delivery networks, while optimizing cache utilization and reducing the need for expensive backend storage, thereby helping you save money. The improved scalability allows companies to serve more users without significant infrastructural investments. And the paper's extension to bipartite graphs and cache networks enable efficient content delivery in edge computing scenarios. With that, we come to the end of our presentation. Thank you.